Okay, yeah. We learned common filter. Okay. There's some theories behind the common filter. You may not completely get the derivation part of the common filter, but today what we're going to do, we'll try to implement it. Okay. And then when you run it, and you'll get a much better idea of how it works. Basically what's the point of using it. Basically what we're trying to implement is this table from the textbook. So we have a system at here with a process noise and a sensor noise. Okay. And the common filter implementation, essentially implement the system and also implement 1, 2, 3, 4 line of code at here. Okay. Yeah. And we're trying to implement using Simulink. So and the system we're going to work with is the system inside the lecture notes. So that's the lecture example number 2 over there. And system matrix G and H are given at here, and C matrix. Okay, this is a sampling time of 0.1 seconds for this system. So basically, once we finish today's lecture, and you can immediately, basically change whatever you have today to the G and H matrix for the project, right? And then you have your common filter, basically. Okay, yeah. I had a handout giving out to you. Basically, what we're trying to implement is we're going to try to implement this system here. So I'll use some Simulink. This is called a subsystem. Okay. Here we have a subsystem representing the actual system here. We have another subsystem representing the common filter. Okay. And inside the subsystem, that's your page, which is this one here. Okay. And this on the back of it here, that's the handout. So if I double click on this, and this is exactly what I show you at here, right? And inside the common filter, basically you have a whole bunch of blocks. That's what we're going to build, okay? And that's basically the inside the common filter. So there's no control at here. So basically there's no control in this system here. So what all you did is you give a certain, well, there is a control, but it's just open loop. So we give in this case we give a sinusoidal system input to the system at here. So with a certain frequency amplitude, and then the system will spit out output. So the system input and output will all be given to the common filter, which is basically an observer, right? And the common filter will try to estimate, basically give out x hat. Okay, yeah. So that's the structure here. Okay, yeah. Okay, so let's build these things together. If you have a MATLAB opened, you need to loading the MATLAB Simulink library. You can type SL capital L library, then browser, probably browse. Yeah, no, a browser. Yeah. So SL capital L, so S small L capital L library browser. Okay. So this will open up this Simulink library right here. Okay. Yeah. I guess alternatively you could just click on the Simulink. Where is Simulink? Yeah, click on the Simulink right here. So that'll bring up that library here. Okay. Yeah. And then you can create a new file. Okay. And then let's save the file right here. Once you create it, let's just save the file. Okay, I'm gonna call it whatever you want to call it. Okay. All right. So now, the most efficient way is we drag all the blocks into our file first, okay, and then we start to connect them. Okay. So if I'm going to use the if I can use a subsystem like what I showed you at here. Okay. So the subsystem. So I need the two basically subsystem like these two modules and signal generators, and then another basically multiplex at here, and then also scope, right? So let's do that. So you go to commonly used block at here. So we need a mux. Sorry, where's my file? So files here. We need a mux set here. We need 2 subsystems. Okay, and we also need a signal generator. Okay, so that you can go to sources, right? Go to the sources set here, so that you can grab a function signal generator here. Which one did I use? I used this one here. Okay. And we need a scope, so let's find a scope. Scope is a sync. So now we need a scope at here. Is that good? Yeah. Okay, so now if you look at the subsystem, for the system we have one input, right? And then system has output Y at here. We also want to have the flexibility output also the state vector x of k. So I do need basically one input terminal and 2 output terminal here, right? For the common filter, I need 2 input terminal and 2 output terminal. So what we can do is we can just go to double click on the subsystem, first subsystem here, and you can delete this one here. So you're going to need lots of things inside here, right? Yeah. Is that good? So now let's basically work on the subsystem first. So this one in here, right? So this subsystem. Okay. And I'll open a subsystem in here. Okay, so this is what we're going to work on here. Let's count it. How many gain blocks do we need? So 1, 2, 3, 4, 5. We need 5 gain blocks. We need 1 over Z here, and we also need 2 terminals. So we need another terminal here. So okay, so let's go to the library at here. Okay. Yeah. Okay, first for maybe let's grab another output at here. So this is out, so another output. Okay. And then we need, how many do we see? 5 gain blocks, right? So 5 gain blocks. So let's go to the commonly used blocks at here. Here's the gain. Okay. Here's the gains at here. So we need 5 of them. So you can just drag one of them into here. And then you can basically control C and start to control V like that, right? Okay, so give you 5 of that. Good. We also need, if you look at, we also need 1 junction, 2 junctions at here, right? So let's grab 2 junctions from the library. And where do we get that here? So it's right here. So it's under the commonly used block here, right? So I'm gonna grab 2 of that into this file. Okay. Yeah. So now if you go back to the main file here, you'll see there are 2 terminals here already, right? Yeah. So let's go back to this. Okay, and we also need 2 random signal input, basically 1 for process noise, 1 for process noise, and 1 for the sensor noise. So we need 2 random signal generator for the blocks at here. Okay. So let's go to source at here. Okay. Then you go down a little bit. Okay. And you'll see there's a random number, so this is the one we can use. You found that? Yeah? Okay, so let's copy 2 of them into our system. Okay. Okay, so I think we can start it now. Okay? Yeah. So we can start basically build our system like this one here, okay? Also, we need another one. Basically, it's a delay block. We need a delay block 1 over Z. Okay. Let's go to our delay blocks, where would it be? So that's typically it's discrete, so it's on the discrete at here. So if you look at here, there's a unit delay block. Okay. So let's take that into here. Okay. All right. So once we finish this, let's connect things up, and you also need some configurations for some of the blocks that are here. Okay. But first of all, let's do the configuration. So the input here, remember input is this, so you can label this basically. This is the input is the U. Oops. What? So you can give a U at here. It is. How do you? Yeah. How do I not let it find anything? Huh? Try to label it. Click on it. Where? Ah, excellent. Excellent. Okay. That's our U here. So you click on the 1, right? And then, okay. MATLAB have evolved quite a bit. Yeah. Okay, and then the U, basically, you see, what we're dealing with is basically U times H, right? And plus G times X of K produce X of K plus 1. So basically, we need to use U or H times U at here, right? So that's what we need. So let's go back here. I need H here, so let's bring a gain block at here. Let's call this is H. Okay, let's call this is H at here. So, and because we need this U input times this, so you can connect these two together. Okay, and then double click on this H at here. Okay, double click on H. Let's just call it in the gain at here. Let's call it H for now, because we're going to initialize later. Okay, I'm going to show you how to initialize. And then here, multiplication is not element-wise, so there's matrix, different matrix multiplication in here. So now, if you think about it, the actual multiplication is what? It's H times U, right? So if you look at the option in here, there's matrix K times U, matrix U times K. U is the input, so we should pick what? This K times U at here, okay, for this part of the multiplication. Okay, so then okay. Okay? Yeah. So that will give you H times U, right? So H times U, so then you connect to this block at here, okay? Yeah, to this block. Before we connect to this block, let's double click on this block here, because we need actually 3 things adding up for this block. 3 things adding up for this block at here. So you need 3 plus signs, okay? 3 plus signs for this block. I don't think I wanted to, so I get rid of the vertical sign there, apply, so that'll give you the 3 plus sign distribute like that. Okay, yeah. So the vertical sign kind of controls where you want to put that plus sign. Okay. So basically 3 plus signs and then okay. Okay. And the first plus sign is connected to this H times U. Okay. So that's H times U, right? Yeah. And then the second block, second plus sign here, that's top one, let's call the top one is G times X of K here. Right? G times X of K. So you can still label something at here, so it's just for yourself, H times U, right? Something like that. Yeah. So I'm going to flip this one 180 degree. To flip, I think it's Control R to flip. Otherwise, you can just right click on it and rotate to flip, and then see you have a Control R here for it to flip it. So Control R. So I'm going to flip it to basically 180 degrees at here. Okay. And then double click on this. This will be our G matrix. So it's G times X. So it's G times the input. So that's basically same as this H block, and then connect to this at here. Is that good? Yeah. Okay, so now you look at another one here, adding what? Adding the process noise here, right? So you should also add the process noise W at here. And then what we can do is we can use the output of this block as the process noise. Okay. You can label that as a process noise. Okay, so first of all, let's double click on this process noise at here. Okay, yeah. So you can see that what this block does is it generates noise. You can set the mean of the noise. You can also set the variance of the noise. Okay, you can also set the seed of the noise and also the sampling time. Okay. Now the sampling time, I'm gonna use a H here representing the sampling time. That's the sampling time that we're going to use. You know, you can change this to any, basically change H to any value to a different sampling time, right? Now what seed basically means is, it basically means how you want to generate this random noise. When you give a seed a different numbers, 0 or 1, so it'll generate a different sequence of random noise. Okay, so you give a 0, it'll generate this sequence. You give 1, it'll generate another sequence. Is that good? Right? But every time when you run this, right, as long as you don't change the seed, it will basically generate the same sequence of random numbers. That make sense? Yeah. So now, for our purpose at here, now if you recall that, if you look at this question, so W at here is process noise, and X is the state vector. So how many state vectors? We have 1, 2, right? So there are 2 state vectors here because the order system is 2. So W here should be what? Should be a vector of a 2 by 1, right? Should be a 2 by 1 vector here. Then that's what RW is basically, right? You know, RW is the variance, basically the covariance matrix for the random noise, and we're going to set it as a diagonal matrix. The diagonal elements will be the variance of the random noise at here, right? So what we do is we're going to keep the variance as 1 at here, and for the seed, right? So we're going to create basically a 2 by 1. So you can the seed at here, really you can use anything. I'll use 0, 1. You can use 1, 0. Really doesn't matter. Okay. So but this is basically telling that random block to generate a 2 by 1 vector at here. Okay, yeah. So then okay. Now, and then I need multiply the output of this process noise with my covariance matrix. That make sense? Yeah, covariance matrix at here. Okay. So this block at here is going to be our covariance matrix. Now, here is a little bit tricky thing. You also have to be very careful here. Okay, so this is a covariance matrix. You can consider covariance, just consider as a variance, right? Consider variance here. So each one of the elements that here is basically representing the variance that here. Okay, but when it comes to MATLAB, when you're generating a certain noise, the variance that here, so this one here, you actually need to enter a standard deviation for this one here. So basically, the way the MATLAB generates the noise is it's the mean plus the standard deviation, then times the 0 mean standard variance of 1 of random noise. Okay, so basically what we need to do at here for this block here, it's actually square root of the RW matrix. Okay, so square root RW matrix, and then you use the matrix basically here matrix the RW times that vector there. Okay, yeah. So K times U and apply. Okay, so we're going to define RW later. Okay, so you can label this as a square root RW. Okay. So then the output of the state and multiply by this. That give us the basically the process noise, basically WK at here. Okay, so WK. Now, alternatively, actually, you do have alternative generating the random noise, which is basically directly enter the variance over here. Okay? Instead of enter a variance 1, you can actually enter the variance directly over here, which basically you will enter a certain a vector here. Let's say 0.01 and 0.01 like that. So that'll basically create the same thing, right? Create the same thing. So you see, you have a 2 by 2 times a 2 by 1. Like what we did here. So you have a 2 by 2 times 2 by 1, you get a 2 by 1, right? And then the original block, if you don't use this block here, if you set it up inside the block, you can also get a 2 by 1. Okay. Okay, so now we got this down here. Okay, so the three things together adding up give us what? Give us this at this location in here. What does that give us? It gives us this basically x of k plus 1, right? X of k plus 1. Okay. And the x of k plus 1 delay by 1 step give us x of k. And this x of k will be used to multiply with the g of k at here. Okay. So this is the G matrix. So that's your, where did it go? That's the G matrix out here, and this is H. So this is basically the system here. See, right? This is basically the system. Okay, and we want to output the system. We want to output the system x of k. So I can take it from here. So this output here will be the x of k. Okay. Right, so this is our system, the state equation, and we also need to create the output equation at here. So output equation. So this one will be our output at here. So now this is your sensor noise at here. So the sensor noise will be used to multiply with the sensor covariance matrix or variance. So if you double click on this, same thing. So 0, 1, 0, you can use 0, 1 here, sampling time. Let's put H at here for now as sampling time. Okay. And let's label this one as our so-called sensor noise. Okay. And then this one is our variance for the sensor. So this is going to be square root of RV. Okay. And then matrix multiplication. Okay. So this times this give us the sensor noise, right? Sensor noise here. Okay. And then for this block, I wanted to actually put one of the plus sign on the top. Okay. So this one needs a little bit manipulation. How do I don't remember now. How do I yeah, there we go. So plus vertical sign. Okay. Separated. This vertical sign is like the angles, trying to separate them for certain angles. So plus vertical sign, and then you get these two, right, arranged like that. Okay, so then connect this here. Okay. So output basically is C times X of k plus the sensor noise. So I guess C times X of k, this will be my C matrix at here. I'm going to explode that a little bit bigger here for you to easy to see. Oh, there's a lot of G here. Okay. This will be C matrix. I'll rotate it 180 degrees like this. So C times x of k. So C times x of k, which is here. Okay. And the C double click. This is our C matrix. So C times input, and then over here, then output is here. So that'll give us our output y of k. Okay, that's it. That's basically your subsystem, which is our system here. Okay? Yeah. Okay, don't forget to save. Is that good? So I'm going to change the subsystem. We're going to call that our plant, or whatever we want to call it here. Okay. Good? Okay. So we're done with this block here now. Now let's get on with the common filter implementation. Okay. So here's the bottom block right here. That's the most sophisticated block. Okay. So double click on this block right here. Okay. Any questions so far? It's all good? Okay. Okay. So for the common filter, if you look at, separate that a little bit here. If you look at what we need, there's a lot of things we need in here. Okay. So we need two inputs and two outputs here. So one. Where's the other output? Oh, yeah, right here. Yeah, right here. So we didn't need two outputs right here, and we also need many blocks. So 1, 2, 3, 4, 5, 6, 7, 8. 8 gain blocks. So let's go to common block here. So I do need 1. Okay, so 8 of them. Okay, and I also need a few junctions out here. So 1, 2, 3, 4, 5, 6. 6 junctions, summation signs. Okay, 6 of them here. Okay, and I also need 2 unit delay block. Okay, so 2 unit delays. Okay, let's work with this together first. Okay, and I also need a matrix multiplications. Okay, so matrix multiplications, what you do need is if you click on the mass operation, there is a product here. So in the mass operation, there's library, there's a product block, and we need 1, 2, 3 of these things. So let's put 2 of that here. Is that good? Okay, let's work with these things. Okay, I need 2 of these, right? Okay, so another thing commonly used. We need 1 in at here, another out over here. Okay, so 2 in, 2 out. Okay. All right. So let's expand this. So you need a little bit more bigger workspace to do all the connections. Move to a little bit to the center here. Okay. Alright, so the input at here is U, so you can label this is the first one. This is our control input, U at here. Okay. And then we're going to use the U times H at here. Okay, U times H. So double click on this. This is going to be our H at here, and then this is K times U. Okay, so U, control U times H, or H times U, I should say. H times U. Okay. So basically we're implementing is this. So we're trying to implement this portion at here. Okay, yeah. So you see there's H times U, right? There's a G times X hat, okay, K minus 1K. Give us X hat K. So this is the prediction part. Remember, the common filter is basically a current type of observer. The first equation is prediction, and the second equation is basically update using the common filter gain times the current output, the difference of the current output and the estimation output. Okay. So these two at here essentially is the common filter, current type of common filter. And then the common filter gain of K is generated from the bottom half right here. So the bottom half K is generated and then faded over here. That make sense? Yeah. So the top one is essentially the model for the common filter, which is these two equations. And the bottom one is how the common filter gain is calculated. Okay. Okay, so and then you can drag another block at here. Okay, so this one we need it to be plus plus vertical. Okay, so connect these two, and I need a gain block. Oops. I need a gain block on the top of it here, and let's flip that 180 degree. And let's call that's our G matrix set here. Okay. Double click on it. Call it G, K times U. Connect to the top of it here. Okay. So these two adding up together, right? These two adding up together is going to be the X hat K minus 1. Okay. And so if you look at this G basically times that, okay, so if you look at the ultimate purpose here is, so this is going to be X hat K minus 1 at here. Okay. So we need to flip this one here, okay, like that, okay, and connecting to the G block set as this. So as I labeled in the handout here, so the signal at here is X hat, that's estimation of the state. Okay, it's at the K minus 1, vertical K minus 1. So that's basically the, it should be enter. Okay, the steps at a K minus 1 here. And then we need another block at here. Okay, so the output at here is our X hat, okay, and K minus 1. Okay, so K is the current time. Okay, so that's the output at here. Okay, yeah. So you can see basically the way we want it to function is the X hat K minus 1 need to plus the common filter multiplied by the difference. So this value multiply this value here give us the X hat KK, right? X hat KK. Okay, so essentially the output at here, Okay, the output at here, okay, this one here is gonna be the X hat K. So that's the common filter output. Okay, common filter, the current estimation, right? X hat. And then you delay this one time, right? Delay it one time, then you get X K minus 1. K. This is X hat. This is X hat over here. Okay, so you delay that a little bit, one step, you get X hat K minus 1, K minus 1. Is that good? Okay. Okay, so second terminal input at here is the Y of K. Okay. So Y of K. And Y of K is the feedback, is the actual system output. Okay, so this is actual system output here, right? And we're trying to use the actual system output minus the estimation system output. Okay? Yeah. So basically, let's put a block at here. Okay. And this block, what we need is we need a one is plus, one is a minus. So you could use plus vertical sign, minus, I think. Okay, let's see if that works. Nope. Oh, I guess I could use this. So you could do this, minus vertical plus. Okay, and then rotate that 180 degrees like this. Okay, so that's not good. So this is minus, should be on the other side. Okay. So plus vertical sign minus. So plus vertical sign minus, and you create a block like this kind of orientation. So this is your inputs at here, and the output this side here is C times X hat. So we do need a basically a block at here. Okay. Let's flip that 180 degree. Okay, so this will be our C at here. C times X hat, right? C times this, K times U. Okay. So in this case, if you look at the formula in here, right? If you look at the formula, it's a C times X hat K minus 1. Okay, C times this. So, all right. C times this, yeah. So let's C times what? C actually times the signal over here. Okay, C times this. And then you connect to this block. Okay. So the output, this is the difference that here, right? This is the difference that here. Okay. And the difference that here, you can label this. The difference is Y of K minus C times X hat K minus 1. Right, so that's the output over here. Okay. As you probably noticed, my label here all dropped down 1. So from K plus 1 to K, or from K to K minus 1. Right. So the formula dropped down just by 1 index. Okay. All right. So and now I need to multiply the output with the common filter gain. Right. So let's put a product here. So this is going to be a matrix product. One side is K, the other side is this signal right here. Okay, so that's going to be this bottom here go to the bottom here. So this top one multiply the bottom. It's always like that. Okay, so the top signal multiplied by the bottom signal here. So the top signal will be our common filter gain value. So we're going to keep that for empty for now. Double click on this. Okay. It's going to be a matrix multiplication, so you select the second one here. So there's going to be a matrix multiplication, then apply. Okay, so that's how you do a matrix multiplication right here. Is that good? Yeah. Then the output, right? The output of this one here is basically you connect it over here. So this is your output here. So that's the common filter gain and then times this y of k minus c times x hat k minus 1. Okay, yeah, that's the top portion, right? So this top portion here is the common filter model. All we need to build the bottom portion, which is to generate the common filter gain k now. Okay, yeah. Okay, so let's generate the bottom portion now. Do you know how to pan it up? How to move up? I need a little more space here. Screw out. Oh, right, middle one. Hey, excellent. Yeah. Okay, so let's build the common filter, the bottom and here, right? Okay. What we're building essentially is the two formulas. One for the common filter gain k, and the other is for these two at here. Okay. Now basically, one is the gain k here, the other is this one plus this one here. Okay. Yeah. Okay. So this building part okay, needs a little bit. So how do we proceed it here? Okay. I guess I need one more block here for the. Basically the process noise RW and also the RV here. So I need two constant blocks. So let's go to continuous, go to the commonly used block and look at the constants. So I need two constant blocks here. Okay, two constant blocks. Okay, so that should be okay now. Let's expand it. So this first constant block is going to be our RW at here. Now I'm going to call this RW1. Okay. The reason is, see, in the system block, we have RW, right, which is the process noise variance matrix. Okay. Yeah. Now in the common filter, you will have another process noise here. You could use different. The rationale is basically. So the rationale is basically you're doing simulation, so the system has a certain noise, which let's say you pretend you don't know, right? And when you design a common filter, you can give an estimation of the system process noise. So if this RW1 is actually the estimation of the system process noise, so this doesn't have to be the same as the actual system noise. So it could be different. Okay, this is actually something we'll play with. And you'll see some different kind of reactions from the common filter here. Okay, yeah. And this one will be our RV at here. So let's use that later here. So let's call this as RV1. Okay. Why this one says 1? Oh, RW1. So this will be RV1 in here. We will initialize all of this later, okay? Yeah. Okay, so first I'm gonna build up this portion here. So G times, I'll build this formula, G times P k minus 1 times G prime. Okay, so building this little portion and then plus RW. Let's build this one here, okay? Yeah. So we can go back to our system in here, drag two gain blocks. Okay, so this, all of this one here, so we can move it down a little bit here. We don't need that. Okay. Okay, so we're gonna call this as our G matrix. Okay. So it's G times U, so input times this. In MATLAB, when you label things, you can't label two things with the same name. So unfortunately, we had to use G1 here. But this is basically the G matrix at here. And this one here is a G prime matrix. Okay, so if you look at the formula here, what is it? It's a G times P times G prime, right? G times P times P prime. So when you double click on this, and we're gonna call this is G prime. So G prime, so this is G transpose. Okay. Now this one will be what? This is not K times U anymore. This is actually what? The input times the gain at here. So this should be U times K. Okay, so it should be U times K at here. Okay, and now you can drag another blocks over here. Okay, and let's double click on this and make it what? Plus, vertical plus. Okay, nope. Make it what is it? Plus. Yeah, that's right. Plus vertical. Okay. And now I connect to here. Connect this. And I connect this. Okay. Yeah. So basically, this is G prime. So whatever here is that G times P, okay, K minus 1 times G prime. Okay. And then plus the process noise. Okay. Okay. So let's do the front one here. Let's rotate that 90 degrees like that. Okay. Yeah. So this will be our so you see here, the signal here is a P K minus 1K here. So then whatever signal over here, this will be P K K. Okay. So this block here got delayed once and give us the P K minus 1 K minus 1 here, right? Yes.
Sorry, just like you said you can't like loop the same thing and put the G1 on there?
Yeah.
Oh,
you
can put a space in it actually.
Oh, you can?
Yeah.
No, what I'm saying is I can't label as a G because I already.
Yeah, with a space.
Oh, can I put space? Okay. Oh. Yeah, you're right. What, you're cheating it. Yeah. Yeah. Excellent. Yeah. Good. So that's this part here, right? Yeah. And then the output set it here. Okay, the output it here. So the output it here is P of K minus 1. Okay, so okay, that's the output, and we're going to use this output multiplied by some more gain matrix set it here. So this will be C prime, or C transpose. So this is C prime, C transpose here. And this will be U times the C transpose. Okay. So that's this one here. Okay. So U times this, which is what? So this portion, right? So C prime times this, and then times C, right? Okay. Let's go back over here a little bit closer. Okay. Another gain block. Okay, so this gain block here will be C now. So this is K times U. Okay, so this K times U now. Okay. Then the output of it here, okay, you will use this one adding up. We look at so you can add up this RV at here, right? Add up the RV. Okay, so adding here and RV over here. So add this up here, right? Yeah. So here is, this is the C times P of K minus 1 times C. So that's this portion right here, and then plus RV. Okay. Yeah. And out of this one here, we're going to use basically the output of this signal needs to be this signal needs to be inversed. Okay. So here's how you do the inverse matrix here. So matrix multiplication, and then you type star backslash. So if you type star backslash for the matrix multiplication, and then what you get is basically star inverse at here. Okay. So we're going to invert the output of this, right? That's basically this portion, see, right? So the inverse of this, okay, the inverse of this, yeah. And then times p k minus 1 times c, right? Yeah. And that's exactly basically the signal over here. So that's the signal over here. Okay. So now this output here is basically the common filter gain, okay? The basic common filter gain, and now we connect it to now we connect it over here. So this is the common filter gain K at here. So this one here is common filter K. Yes. Double click. It's a matrix multiplication. Type multiplication sign and the backslash sign. Got it? Yeah. Okay. Yeah. All right. So we got most of the part at here already, right? We just need this second portion, P of kk equal to P of kk minus 1. This one at here. So why don't I just copy over here? Okay. So we just need this portion now. Okay, that's how we're going to build at the bottom and here, right? Okay, so here is a P of k. So this is a P of k minus 1, which is this. And then we're going to use this signal multiplied by C times this. So I need a gain block over here. Okay, I need this one multiplied by this signal. And that's your C matrix. Okay, and this is your K times U. So whatever input, right, the C times whatever the input here. So that's C times this. Then the output of the C times this will multiply with the gain matrix K, right? Gain matrix K here. So I guess I need where's my other matrix multiplication? I thought I brought how many? I missed one here. How come I can't scroll it in anymore? That's weird. How come I cannot? Anyway, so let's use another matrix multiplication in here, and then let's invert that 180 degrees. What's going on here? How come I cannot even invert? Oh, it's too much. Okay. Up a little bit. So this matrix set here is the bottom. The gain matrix K is at the top right here. So gain matrix, this is your gain in here. I got it here. Yeah, let's get rid of that. Right. So that basically it's the K. The top one is a K times the bottom one, which is a C. C times P of K here. Okay. Then the output is this. Given to, so flip that 180 degrees, and make it plus, vertical plus, no, remember this, okay, yeah, so make it like this orientation. So here is this portion, and here is this signal at here. Okay, so these two give you the second one here. and then you can connect to here, right? Okay.
For that last one.
Yeah.
You need the minus.
Oh, I need the minus. You're absolutely right. Absolutely. Okay, great. This is minus RW1. So this one here, these two noise, we're actually going to try different noise from the actual system process noise. So you could do that. Basically, you think about the actual situation. Well, I don't know what the actual process or sensor noise, right? Yeah. And of course, simulation, you have to give certain values. But when you design common filter, these two are what your actual guess, actual estimations, right? Yeah. So that's why these two would be different from the actual system process noise. So that's it. You see, right? Oh, I need one more output here. So output, we're outputting y hat. So where's my y hat at here? So y hat is over here. Sorry, where's y hat? Yeah, y hat is over here, right? So y hat, this c times the c times your x hat is, this will be the y hat right here. Okay. Is that good? Yeah. Okay, so now everything's ready now, and what is it? Okay. Now there's a couple of things you have to be very careful at here. Okay, it's the initialization. Okay, let's go back to this. Finish this block at here. Okay, let's go back to the finish this block. Okay, so if you finish this block, basically the input, give it to the U, the input here, so just like that. So input, give it to U at here. Same thing, the U will be also given common filter. The subsystem here, you connect to the Y of K at here. And then we're gonna compare my Y hat and also the Y at here, so it's like the estimation output comparison, and then give it to the scope. Okay, so that's what we're going to compare. So that's it. Okay, yeah. Okay, so let's start from the signal at here. I think we can use 1, that should be okay. The unit here, let me just check here. What do I use? So 1 reading per second, so that's fine. Okay. Okay, so let's go back to the plant here. Okay, go back to the plant. One thing you need to basically initialize this. Double click on the 1/z block. Okay. So this is where you can initialize the initial condition. So remember, this is your system, right? This block here. So we have initial condition x0. You can initialize initial condition to anything you want. You don't have to be 0. So we have a vector of 2 by 1. So I could just use even 1, 1 here for the system initialization. Okay. I don't think column or row vector matters at here. So somehow, yeah, you can try it. Remember, it matters. So that would be my initial condition, right? Initial condition for the system. The sampling time -1 basically means you're taking the sampling time from the previous block. You inherit the sampling time from the previous block. And you could just use h as x sampling time. If you use -1, that's still okay. Okay, yeah. So let's maybe change the h here. Okay. 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 So that's the system side here. Override. Okay. And then you go to the common filter at here. Okay. You go to common filter, same thing. For this 1/z block, we need to initialize that to certain initial condition. This is observer's initial condition, right? Now, observer initial condition doesn't have to be the same as the actual system initial condition. So you could use a 0, 0 in here to make it purposely different from the actual system initial condition. Okay, yeah, and then also for this one of Z block right here. Okay, so this one of Z block is basically P of KK to P of K minus 1, K minus 1, right? So we also need to initialize this block. So that's P naught. So that's the one we, if you recall that, right? That's the basically the covariance matrix. So the P here, okay, the expected value, okay, of estimation error. Okay, so that's initialization of this part. Good. Okay. Okay. So finally, another initialization. Okay, remember we have all of system parameter G, H, C, RW, RV, right? So we need to initialize that before we run the system. Now there are two things you can do is you can create basically initialization file, and you run it every time before you run the Simulink. Okay, so this is basically the simulation here. And then, or the other way you could do is, I'll show you this one. This is a better way, I think. You go to View, Models Explorer, and then the Model Workspace. So go to View, Model Explorer, and then Model Workspace. Okay, then select that one there, and then over here it'll pop up this Model Workspace here. Okay, and then you can choose. Let's give you a little bit of time here. You can choose MATLAB code. Okay. Then that's where I copied those things into here. Okay. So you can type in here. So H is this GH. That's from the example. C is 10. RW RV. Right. Pardon me? That's a good point. I'm not sure how to do that. So why don't I just a second here. Magnification. Oh, magnifier? Here? Oh, there we go. Yeah. See, every time learning something new here. Yeah.
What is P naught?
P naught. Oh, right. Oh, I didn't have a P naught here. Yeah, we need to type in P naught here. You're right. Yeah. So let's type in P naught because I need to type in over there. But you can type a P naught. Anything you can. So 10, for example, 0, 0, 10. Yeah. So that's the your estimated estimation error covariance matrix. Yeah. If you have a bigger number here, basically you don't have much of confidence. Yeah. If a smaller number, then you have a good confidence. Yeah. That's a good point. I need to copy that into my workspace. Oh, I can keep this one here. Excellent. Okay, let's put a P naught over here. Okay. Yeah, once you finish this, you need to reinitialize from the source. Basically, initialize. It's like running the code. So you'll see this shows up over here, right? Yeah. So the advantage of doing this is basically every time when you open up the Simulink file, then all of these parameters will be automatically initialized, and then you don't have to, oh right, forgot this, forgot that, right, that type of things. Okay. Are you done with this? Yeah. So you're ready to run. And 99% the first time won't work. Yeah. And there, if you're lucky, it'll work. But it never happened, never worked the first time when I ran this. Yeah, even though it's many times I'm doing. Okay, so you could run it now. I will close this one first. Go back to our Simulink. Let's see, does it run? Oh, it actually runs. Okay. Yeah, so actually it's good. So it's running, right? So we're seeing something at here. Do you see what I see? Yeah? Okay, so we can interpret this, right, a little bit as to what it means. Let's give it a little bit longer running time here. Instead of 10 seconds, let's make it maybe 20 or 30 seconds here. Yeah? Okay, so let's take a look at the running out of here, right? The results out of here. Okay. Take a guess. Which is which? What do you think the yellow one is? The system sensor output, right? Yeah. And the blue one is the common filter. Okay? Yeah. So over here, yeah.
Hey, the DC gain is a bit low.
There's actually no control. You see here, there's no feedback, right? Yeah, there's no control, no feedback here. This is purely open loop. So my sinusoid will give the system here, right? If you want a feedback now, then what happens is your common filters here, then instead of directly give the sinusoid to the U actually is generated by what? You need a feedback gain at here, and then gain multiplied by the common filter x of k, and then the output of the gain give it to the U at here, right? Yeah. That's regulation, just like any other pole placement or LQR, right? Yeah. So let's go back to the results today here, right? Now, before we move ahead, can you take a look at in the model space? In the model space, the value we entered. What is the R? You see here, I entered RW1 to be the same as RW, right? And I entered RV1 to be what? To be actually 10 times more than the actual sensor output. Okay? Yeah. If you recall at the end of the previous lecture, and actually we're trying to intuitively trying to take understanding of the common filter here. So RW is 0.001. If I multiply the RV by 10 times, guess what? The ratio between RW and RV must be very, very what? Small, right? Very, very small. Or in other words, if you compare for the common filter, if you compare the RW1 and RV1, the sensor has so much noise in it, right? The sensor has a lot of noise at here. So in this case, I want you to try yourself. Basically, try to do this step here. Very easy. See, this is a common filter, isn't it, right? You go to the commonly used block right here. There should be a workspace. Where's the workspace? Maybe it's the source. Sync. Under sync. Under sync. Yeah, there's a workspace right here. You can output the common filter value okay, to the workspace. Okay, you can look at what the actual common filter gain is at the workspace, or even just put it on a scope. Okay, yeah. So, given the current RW/RV ratio at here, okay, given this ratio at here, okay, this ratio, as we discussed in the previous lecture, the common filter gain should be quite small, because it's not trying to amplify the sensor, because it's too much noise, right? Yeah. So that's actually, in this case, when you look at the scope, what does it remind you? The input-output here, basically, what's between the input-output? So like there's what? Between the input-output, there's like a low-pass filter, right? So that's basically what common filter is doing in it here. Okay. Now what about, let's do this, right? Let's try go to the models Explorer workspace at here. Okay, now let's try this. Let's, instead of multiply by 10, let's divide this by maybe 100. Okay, let's divide this by 100 here. Okay. So now this time, what does the common filter, from a common filter point of view, the common filter thinks the sensor noise are actually not too much anymore, right? It's comparable with your process noise, then, isn't it, right? Yeah. So if I do this, then what happens when I click on the simulation? Do you see what they say here? Yeah. So now what happened? The blue one now is less low pass, and then the blue one actually now trying to do what? Trying to follow the yellow one now, right?
It listens to the noise.
Exactly, right? So this is more like the common filter now. This time, what it's doing is trying to actually doing a much better job in terms of estimating the system outputs, right? Yeah, it's trying to follow the system output basically, okay? Yeah. Or trying to do a better estimation job. So that's something when you do simulation, right? Then you can always manipulate your RW1, RW1 and RV1, okay, to better tune your system, basically. Okay. So now, in terms of the project, then I think it's quite straightforward. Then all you need to change the G matrix, H matrix, right, and also the sampling time to your actual sampling time. Then you get your common filter basically. Now, in terms of the control, then what you do is basically there are two kind of control you could do. One is the regulation problem. The other is the reference control problem. For regulation problem, so you can insert a gain block at here, and then use the k multiplied by x of k here, and this time it's negative, right? And then you output this one here to the control signal at here. Okay, so that gives you the regulation problem. Okay, and for reference control, then you need a basically reference control input, and then the k naught. Remember that DC gain k naught, right? And then put the junction in here plus this, then you get your reference control. Okay, yeah. So common filter plus this k. If this k is generated based on your LQR command, then this is basically what we call the LQG. Okay, yeah. Is that simple, right? When you do this actual experimentation, you take out the plant, okay, take it out, use the orange one in the template, and you don't even have to change this, okay? But of course, the GH right here has to be the same as your mathematical model, right, for the plant, okay? And then you get your experiments, okay? Yeah. Is that okay? Yeah. Okay. So we only have one lecture left. For the next lecture, I think I'm going to help you guys. I think everybody kind of burned out here. If you're interested, I do have one more lecture content I can tell you, but I think if we best use the time, I'll help you guys with the project in the next lecture. Okay? So we can either do it here or do it over there, but there's only 3 setups here. So I'm going to come over here, and if you have questions on the project, then I can answer your questions and simulations or experiments. Okay?